Okay, welcome to the third video in this series. So in the previous lecture, we talked about Laplace transform, how we can take a function and extract some information about its rotational and decaying aspects and embed those information in the S domain or in a complex S plane. Now, the reverse of that is to take those information and reconstruct the function back into time domain using the existing knowledge that are available to us in the S domain. So this is a very important and necessary step in closing the loop. So we take usually a function or a set of equations describing a function, take those to S domain, do some calculation that we'll get into, figure out what features are available in the function through information in the S domain, and then use that to reconstruct back the function. So that is the purpose of an inverse Laplace transform. This is the definition of inverse Laplace. If you remember, Laplace transform was a simple integral from 0 to infinity, f of t e to the minus st dt. You would expect to see some reverse of that, so e to the plus st fs ds integral over s. But as you can see, it is a lot more complex integral. So first of all, you have to first calculate integral for some time, some t, and then take the limit of that, increase the bound of integral to infinity. And this gamma has a lot of baggage attached to it that really makes this inverse Laplace quite cumbersome to work with. So in practice, I don't think anybody really uses this form. There are easier, more intuitive, and more practical ways to calculate the inverse Laplace. So let's see that in an example. So let's do one example. So take my f of s to be s plus 3 divided by s plus 1 times s plus 2. That's my whatever mysterious function that I had. I took the Laplace transform, I arrived at this formula for the function. Now the goal is to use this and go back and find what the mysterious function was. We can try to use this, but let's not do that. Instead, I'm going to simplify things for myself. So I'm going to write this f of s as essentially break out this fraction into two fractions. 2 is going to be 2 over s plus 1 and minus 1 over s plus 2. It's the same function. You can verify it for yourself that this works. Now remember, Laplace was a linear transformation. I'm going to write it here too. Laplace inverse is a linear transformation. So essentially, when I want to find the Laplace inverse of f of s, this is equal to Laplace inverse of 2 over s plus 1 minus Laplace inverse of 1 over s plus 2. And these are Now, relatively easy if you look at our table of functions and their Laplace transform. This 1 over s plus something has the form of e to at. So again, 2 is a constant, and I can take that out. What I end up with is 2 times Laplace transform of 1 over s plus 1 is, where is it? This is e to the minus at, this is my a, minus at, which is minus 1t, minus, this is 1 times, well, I didn't need that, e to the minus 2t. So really, with this simple trick, I could reconstruct my f of t to be 2 e to the minus t minus e to the minus 2t, without trying to use this integral to calculate it. So one thing, again, I want to hint out, maybe useful to reiterate, see what happens. I had this polynomial, s plus 1 times s plus 2, and see how it related to the function. So the roots of this polynomial, s equals minus 1 and s equals minus 2, define the characteristic modes of my time series signal. So the poles, remember where f of s was infinity, equivalently when the denominator was 0, equivalently these are the poles. Poles of a function f of s defines how the function will look like in the time domain. Okay. So this is a very useful and practical way to calculate the functions of time, taking the Laplace transform of their f of s. All we need to do is to transform our f of s, whatever function it is, into something that we know the corresponding time domain functions for those pieces of chunks of function. So we should use the linearity. We should take f of s, break it into chunks, and take those chunks with easily calculable inverse to get that. The question is, how do we systematically go about doing that? If we have a general f of s, how can we break it into these pieces? So one good thing about functions, real functions, real as opposed to imaginary functions, all the functions that we work with will end up with Laplace transforms of the form some polynomial b of s divided by some polynomial a of s. This is true for most of the functions that we are dealing with. Well, everything that we deal with in linear systems. And we can really break that. We can have just a constant value and s plus z1. These are the zeros of the function f of s, to s plus zm, and it will have some poles, s plus p1 S plus P2 dot 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 S plus Pn. So I have n poles and m zeros. So this is already a good starting point. The next step that we have to take is make this form into something that is more manageable. We usually don't have a general form of this form. We can't find it in our table. But we can do something and convert it to something called partial fraction. A2 S plus P2 to an S plus Pn. The good thing is, if we have a function of this form, we can always convert it to these partial fractions. Now the question remains, how do we calculate these AIs? Again, going back to the idea of poles, you will see when we have these partial fractions, the poles will eventually define the modes existing within the original f of t signal. And finding these A's are decently simple in two ways. You can do it two ways. There are pre-built MATLAB functions. We'll get to those in class, that you can input your original f of s. It can spit out all these partial fractions. But they are, the procedure is simple enough that we can try it by hand. So we have this f of s. We want to find these AI. For instance, one of them A1. What we can do is multiply both sides of this by the denominator of that, the pole associated with that partial fraction. And I get S plus P1, S plus P1 times f of s equals, if I multiply both sides by s plus P1, this one cancel. So I have A1 plus s plus P1 A2 over s plus P2 and all other terms. Now if I evaluate both sides at s equals minus P1, see what happens. All of these terms on the right hand side that have s plus P1 will cancel, will be 0. So on the left, on the right, I only have A1. And if I evaluate this product, s plus P1 f of s evaluated at s equals minus P1, that would give me A1. We can do the same thing for all different AIs. Given a few conditions that we'll get to those, that there are no complex poles and there are no repeated poles. For instance, there are no one that has power, some power, how do I write it? Power R, for instance. We will get to those repeated poles in a minute. So if you want to see this in practice, let's go back to this example. Try to work with this original function and try to get at this form. So my f of s equals this. I'm going to write it as a1 s plus 1 plus some a2 s plus 2, the two poles. Now for a1, I'm going to multiply both sides by the term associated with this pole, so s plus 1 times f of s equals a1 plus s plus 1 a2 over s plus 2. And I'm going to rewrite this s plus 1 times f of s. Using that, it is s plus 3. This s plus 1 cancels with that one, s plus 3 over s plus 2. Now put s equals minus 1 on both sides. On that side, I only have a 1. On this side, I have minus 1 plus 3 over minus 1 plus 2. That is 2 over 1, which equals 2, equals a1. It's same as this. Similarly, for the second one, I multiply both sides by s plus 2. So if I do that, s plus 2 f of s, which this one is s plus 3 over s plus 1. This equals a1 times s plus 2 over s plus 1 plus a2. Evaluating at s equals minus 2 gives me 1 over minus 1 equals a2, which is the same as this. So it is fairly simple to work with these partial fractions, convert your original fraction of some polynomial of s divided by another, convert it to these partial fractions, and from there calculate the Laplace transform of individual fractions. So let me clean up the board and we'll see what we can do if we have repeated poles and if we have complex poles. So see you soon. Okay, welcome back. So there are two cases that we want to consider. One is when we have these complex conjugate poles that always show up in pairs, and also when we have repeated poles. So there are multiple powers of the same pole. So let's first focus on complex conjugate ones. If there are complex conjugate poles, we usually do not want to break them up into this form. The reason is if we try to do this and we want to calculate A's, for instance, we have to multiply both sides by sigma plus j omega to get A1, and then put S equals minus sigma plus j omega. If we evaluate that, we'll end up with a complex coefficient for AI, which transferring that to time domain gives us a little trouble converting it to a real function. The fact that there are always complex pairs resolve that, but we don't want to get into those trouble. So in these cases, we often like to stay away from breaking these poles into individual complex conjugate forms, and we want to stay at these second order fractions. For instance, s, what do we have? S, I don't know, S2 plus something, C1s plus C2. You want to work with that form because it makes it a lot easier. Let's do a quick example of that. So my f of s equals 2s plus 12 divided by s squared 2s plus 5. So this function, the poles of this are the two poles, complex conjugate poles, are p equal s minus 1 plus minus 2j. So this is one example that we do not want to do that. But there is a nicer way to go about this condition. Remember that this is a reminder that in our table we have Laplace transform of e to the minus st. You're seeing my neck. E to the minus at, I'm sorry. At sine of omega t, Laplace transform of this is omega over s plus a squared plus omega squared, and Laplace transform of e to the minus at cosine of omega t similarly is s plus a over s plus a squared plus omega squared. So we have already this and a few other forms. It is easier to try to transform this second order fraction into a combination of these two and then use these forms to get the original f of t. So what I'm going to do, first realizing that s squared plus 2s plus 5, this is s squared plus 2s plus 4 plus 1, so essentially s plus 1 squared. Let me just double check I'm not making a mistake. Yes, plus 2 squared. So this form, s plus something squared plus another thing squared, fits nicely with that. What we remain to do is change the numerator to give us similar form as that. So if I take 1, 2 out, so I want to construct something that involves this s plus a or s plus 1. So I take 2 out, I'll have 2s plus 1. That leaves us with another 10 left over. So f of s can be written as 2 of s plus 1 divided by s plus 1 squared plus 2 squared plus 10. And again, to be more consistent, I'm going to take out a 5 from here and a 2 divided by s plus 1 squared plus 2 squared. Just go over this again on your own. Make sure you follow how we arrived at this. And now this is exactly the same forms as those. So Laplace transform of this, or f of t, is going to be 2 e to the minus t because a is 1. This one was cosine. Our omega is 2, cosine of 2t plus 5. This one is the sine version, e to the minus t sine of 2t. Let's put this here to be consistent. And that is the final answer. So it is a relatively easier way than trying to go from the complex variables and then combining those to end up with a real version. Okay. All right. So the next order of business is dealing with repeated poles. When we have poles that have some power n, first of all, we call them a pole of order n in this case. So the rest of them could be either complex conjugate poles or simple poles with just order 1. So those can be handled with the previous methods. But let's focus only on this repeated pole. That I'm going to write this, forget about the rest. I'm going to write it as another set of fraction, b1 s plus p1 plus some b2 s plus p1 squared until we reach the order n. bn s plus p1 to the order n, to power n. So I again went further and broke this into these partial fractions. As before, we are trying to find the coefficients b's. So there is a fairly systematic way to handle that. First, we start with the highest order and we multiply both sides by s plus p to the power n, s plus p1 to the power n, f of s equals, I have b1, one of them cancels with this denominator, so I end up with power of n minus 1, s plus p1 to the power n minus 1, plus b2, now 2 of it cancels, so I have s plus p1 to the power n minus 2, plus dot dot dot, b n minus 1 times s plus p1 plus bn. Now with this, the last one is just a number. So if we set s equals minus p1, all of these will be 0, and we can evaluate that, the left-hand side. So s plus p1 to the power n f of s, evaluated at s equals minus p1, gives us the last one, bn. So one is out. What about the rest? In the next step, what we can do is start from this equation and take a derivative with respect to s. Let's see what happens. So if I take d over ds of s plus p1 to the power n f of s, that side is good. The other side, I have n minus 1 b1 s plus p1 to n minus 2 plus, we take derivative, dot, dot, dot. We reach to the last two. The derivative of this term is only bn minus 1. And that one is 0. Now if we evaluate the first derivative of this term at s equals minus p1, that should give us the second to last. So d over ds of s plus p1 to power n f of s, this evaluated at s equals minus p1, gives us bn minus 1. We can do that. And then we can continue taking derivatives. Continue derivatives. And in each step we can calculate one of the b's, the last remaining one. And that one is going to be b, well, k factorial. Let me be a bit more clear. For bk at some in the index k, I have k factorial bk will be equal to the kth derivative, dk over dsk of this s plus p1 power n f of s, evaluated at s equals minus p1. So with this is a systematic way, starting from the highest order, and then the next derivatives, we can calculate all the b's with relative ease. It could be long, but it is systematic, and we can calculate that. So let me clean out the board because there is not enough time, enough space to do an example, and I come back when the board is clean. Okay, so let's look at this example. We have a pole of order 3 at s equals minus 1. We want to find the coefficients b1, b2, and b3 to reconstruct this fractional function. So what we can do is multiply s plus 1 cube to f by fs, fs times s plus 1 cube. It is going to be b1 s plus 1 squared plus b2 s plus 1 plus b3, and here I'm going to evaluate the calculate this f of s times s plus 1 cube, cancel out with this, so this one is s squared plus 2s plus 3. Now in step 1, to calculate b3, we evaluate this. S squared plus 2s plus 3 evaluated at s equals minus 1. This becomes 0, that becomes 0. On the other side we have b3, and put in minus 1 is 1 minus 2 plus 3, that's 2, equals b3. So that's the first one. Let me maybe put number. Step 1, step 2. Now we take derivative of this with respect to s. So d over ds of that s squared plus 2s plus 3 equals time derivative, s derivative of that. So I have 2 b1 times s plus 1 plus b2. This thing is 2s plus 2. So I evaluate 2s plus 2 at s equals minus 1. On that side we have b2. On this side we have 0. So b2 equals 0. And the last step, 3, I take another derivative of this, d over ds of this line 2s plus 2 equals derivative of that. It's going to be 2b1. You take the derivative, it becomes 2. Okay, we really even don't need to put any s value because there's no s value. 2b1 equals 2. So b1 equals 1. So in the end, my function f of s equals, what do we have? 2. Now let's start from here. 1 over s plus 1 plus that one is 0, so we skip it, plus 2 over s plus 1 cube. And from here, the time series, the first one is e to the minus t. The second one is 2 times 1 over s plus 1 cube. And if you go back and look at the table and properties of Laplace transform, if we have a power 3, means that our original function was 1 power less, so t squared times the same thing. There's also a coefficient, so this 2 here, the Laplace transform of that from the table is 1 over 2 factorial t squared e to minus t. And cancelling all of that is going to be e to the minus t plus t2 e to the minus t. And that is the final answer when we have these repeated poles. Okay, now we have all the tools we need to solve a differential equation easily. Okay, let's do an example. This. So let's look at it through an example. I have this cart and pendulum, mass spring damper system. There is a spring attached to a car. This one has mass m, and that one has a stiffness k. A very simple linear system. If I draw the free body diagram of m, let's forget about the forces in the vertical direction because they're going to cancel out. So the only force acting on this system in the horizontal direction is some force, F. I'm going to annotate this. So from the wall, I'm going to put the distance of the mass from the wall, call it x. Oh, maybe you can't see it too far up. Call it x. So a few conditions, let's pretend originally at the beginning x of 0 equals 1, and the system starts from rest. So velocity at the beginning is 0. Essentially, this means we are pulling it and let it go. And what else? There was something I wanted to mention. Oh, for the spring, x naught of this spring, or let me call it another name, L naught, the resting length, equals 0. Resting length. So with all this definition, let's solve this, the movement of this mass and a spring system over time. From the free body diagram, I know MA equals minus F. And be careful about it's very useful to properly define position. So through this notation defining x, I've already mentioned that positive is to the right. So if acceleration is positive to the right, my f with this direction that I draw it here is negative. And f here, if starting from 0, this is 0, length 0. If I pull x in positive direction, the force of F is going to be, oops, this should be K. K x minus 0, 0 being the resting length. So this is going to be Kx. And we know acceleration is the second derivative of position. So mx double dot, I take k to this side plus kx equals 0. This is what we call equation of motion. Equation of motion. And it's a second order differential equation that describes how this body moves over time. We want to solve this. We want to find x of t. There are other classical methods to solve this. For instance, you can think of what kind of function function x has the same form as its second derivative. In that case, a sine function would work, because sine, you take the second derivative, becomes minus sine, but remains its shape, and we can try to figure out what is the coefficient behind that sine and what is the frequency of it and all that. But let's use Laplace transform to solve this. What I can do is, now I have this relationship between function x and its second derivative. If I take Laplace transform of the entire equation, mx double dot plus kx equals 0, because Laplace transform of 0 is 0, and because Laplace transform is linear, that gives me m Laplace transform of x double dot plus k Laplace transform of x equals 0. From the properties of Laplace transform, we know what Laplace transform of x double dot is. So I have m. This is going to be s squared x of s, where x of s is Laplace transform of x, minus s x of 0, the initial condition in position, minus x dot of 0. And the rest I have k, Laplace transform of x is capital X of s equals 0. Now you see the power of Laplace transform. We transform the differential equation to an algebraic equation involving the function of s, x of s, and some numbers and variable s. So if I isolate or factor x of s, I have ms squared. Or before that, from the initial conditions, x dot of 0 we said is 0, x of 0 we said is 1. So these to simplify, I have now continue with my factoring. I also have one k over there. That checks out this term, that term, this one's 0. The only thing remains is, I'm going to take out the other side, is s. S times 1. So from here, x of s is s over ms squared plus k. So let's take a moment and see what happened. We had a differential equation. We took the Laplace transform. Essentially, we took our differential equation to the domain of the S domain, the domain that contains these decaying, oscillating functions. And among all possible, infinitely possible combinations of x's that may exist, the differential equation enforces some structure or some constraints, enforcing it to take a certain form that is compatible with the definition of the differential equation. So essentially, this differential equation is putting constraints and shaping these modes such that only a certain set of them are now become compatible. And that is defined with this form. So that's what really is happening here. Let me do a little bit of simplifications, not too much, but I'm going, oh, it must be ms, because there was one m here. So I'm going to divide the top and bottom by m, so it becomes a little nicer, s squared plus k over m. Now I have this x of s. Now you compare it with, let me also write it, s over s squared plus, I'm going to call this omega n squared, where omega n squared is k over m. Now this is a familiar form. This is the Laplace transform of cosine function. So from here we can see x of t is cosine of omega n t, where omega n is the square root of k over m. This is called natural frequency of the system. And the response, it turned out to be a cosine function. So I'm going to draw it slightly differently to be compatible with that shape. So originally I had this mass here. So I'm plotting x as a function of time. This is time. So I'm rotating the usual function that we had. And it's going to look like this. the math just, well, I shouldn't have done it like this, but it's okay. So let's pretend it looked like this. The 0 is here. So the math just goes back and forth from this reference position 0 over time, and it never settles. So that's the way we can use a very simple example, the way we can use Laplace transform to solve differential equations and define characteristic modes of a system's response. In this case, it was a sinusoidal function with frequency omega n. And omega n was dependent on the parameters of the system, the mass and the stiffness. So let me see if I have anything else. So again, going back to poles, I try to reiterate this many times, hoping that the idea is reinforced. What defined the mode of the system was the poles of this denominator. The denominator is called characteristic polynomial. So this polynomial, this is called characteristic polynomial or characteristic equation. It is very fundamental because it defines the modes of the response of the system. And where did this come from? From the structure of the differential equation that was revealed through Laplace transform. So through all of this mess, I hope you can see the value of Laplace transform in not only solving differential equation, but learning more about these existence of characteristic mode rather than just looking at a final answer. This method gives us more insight into the response of the system. Okay, so that is it for now. This is all the preliminaries that we need to start dealing with real dynamical systems. And in the next few lectures, we dive into modeling different mechanical systems and using these methods to describe their behavior over time. So until then,